Hello, beautiful people. Today we're going to be talking about 7.5, solve special types of linear systems. So you've already know what the norm is, and so sometimes we'll have that, but there are some special cases that you haven't quite seen yet. So that's what we're going to look at today. We're going to read here the number of solutions. The number of solutions of a linear system, that's going to be the relationship between the graph of the linear system and the system's number of solutions as described below. So this chart will pretty much tell us everything that we need to know. So here's what you've seen before. You've seen where you've had two different lines and then they intersect at one point. These lines intersect at one point. That's one solution. One solution, they intersect at one point. Now what's special is what we're going to see today is if a solution or if a system has infinite many solutions. So if we know that they have one solution when they touch only one time, then infinite many solutions would mean that they have to touch infinite many times. And so when would two lines touch infinite many times? If they're the same line. So like right now, I'm pretend like I'm drawing another line, but when are they going to touch? At every single point, from here to here to here to here to here to here, all the way to infinity. So these lines, in your book, it may say that they coincide. But that basically just means that they are the same line. Same line means that they have the same slope and the same intercept. So for this, if you're solving algebraically, you would have some number equal to the same number. You'll see that in a little bit though. And then there are also times when there's no solution, absolutely no solution. So if you're talking graphically, instead of them crossing at one point and instead of them crossing at infinite many points, these will never cross. And so what lines will never cross or will never intersect? Lines that are parallel. So lines that are parallel. And then remember, parallel lines have the same slope. Excuse me. And so if you're solving algebraically for this one, you're going to have a number equals a different number. Some number equals a different number, like 0 equals 5. That's not true. It's never been true. So you would say no solution in that case. So let's check out some examples if you don't mind. Graph the linear system. Then use the graph to tell whether the system has one solution, no solution, or infinite many solutions. So I have to solve this by graphing. So I'm going to solve for y. Negative 9x plus 6y is equal to 18. Remember when you're solving graphically, y equals mx plus b is my key there. So I'm going to solve for y to get this in slope-intercept form. So I will add 9x and add 9x. And I have 6y is equal to 9x plus 18. At any time, if I'm going too fast, you go ahead and press pause. Or if any time you want to just do this for yourself and use me to check yourself, that's welcomed as well. I'm looking at these two, and I'm going to simplify 9 over 6 by dividing by 3. So I get 3 over 2x plus 3. So I'm going to graph that. My slope is 3 over 2, and my y-intercept is 0, 3. So you're going to start at 3, 1, 2, 3, and place your dot. From here, you're going to go up 1, 2, 3, and right 2. Up 1, 2, 3, and right 2. And then if you would please connect your dots. And then you're going to do the same thing for the other equation now. So solve for y if you don't mind. You have 6x minus 4y equals negative 12. Minus 6x minus 6x. Negative 4y is equal to negative 6x minus 12. From here, I'm going to divide by negative 4 to each and every term. And I have y is equal to 3 over 2x plus 3. My slope is 3 over 2. And my y-intercept is 0, 3. Sounds familiar? It kind of should. So for this line, I would start at 1, 2, 3. and then I'd go up 1, 2, 3, and right 2. And you will find that you are on the exact same line yet again. You don't actually have to draw both of them like one on top of the other. But the question is, when do these two lines touch? Well, they're always touching because of the same line, Miss Fitzgerald. So I would say that this has infinite many solutions. You may also write just many solutions. That's acceptable, but you can't just say solution. At minimum, you can say many solutions. All right, keeping it moving. Same directions as the last one, so I'm going to do what we did before and get each of these into slope-intercept form. So x plus y equals 5. I'm going to minus x and minus x. And I have y is equal to negative x plus 5. So my slope, they don't give me a number, but I know that there's a 1 in front of there, is negative 1 over 1. And my y-intercept is 0, 5. So b is still where I begin. So I'm going to begin at 1, 2, 3, 4, 5, and place my dot. And from here, I'm going to go down 1 and right 1. Down, right, down, right, down, right, down, right, down, right. That's down, right. Crazy. So then you're going to connect them. I've never thought about that. Sorry. Made myself laugh. And that's my first line. Now, I think you and I both might appreciate the second line just a little bit more because it's already in standard form for us. I'm sorry, in slope-intercept form. So for this one, y equals negative x minus 5. I can tell that my slope is negative 1 over 1, and my y-intercept is 0, negative 5. So 0, negative 1, 2, 3, 4, 5. The other one was positive, so they're not the same line. And then from here, I'm going to go down 1, right 1, down 1, right 1, down, right, down, right, down, right. It's downright amazing. And then you will connect your dots. I'm going to start using that term, downright. And when will these two lines intersect? Never. Why? Because they have the same slope. We could really kind of see that as soon as we identified the slopes. So because they have the same slope, they will never intersect, which means that we have no solution. If they did cross at a point, I would just write that coordinate as you did in 7.1. So no solution for this one. Okay, the next one, solve the system using either substitution or elimination. This is where you now have a choice. You can pick whichever method you like, whichever one looks easiest to you. When I pick, I'll show you, or I'll tell you what goes inside, what happens in my lovely little mind. And you can see why I pick what I pick. So for number 3, 2x plus y equals negative 3. And y is equal to negative 2x plus 5. So my two choices are substitution or elimination. For me, it makes sense to pick substitution. Why? Because one of the variables is already isolated. So from here, I can take this here and plug it in here. So I have 2x plus, and then my y is equal to negative 2x plus 5. And then changing colors, I think it looks great, but it's kind of inconvenient. Equals negative 3. So I just replaced this y for this value, substituted it in. So this is nice because I didn't have to distribute anything here. So this is just 2x plus a negative 2x plus 5 equals negative 3. You can skip this step if you want to. What is 2x minus 2x? 0. So this is gone. And I am left with 5 equals negative 3. Does 5 equal negative 3? Not today, not yesterday, and not ever. So for this one, I'm going to say no solution because I have one number equaling a different number. Now, number 4 is a lovely review of 7.4 because I think it's going to be wise to do elimination for this one. I love substitution if I have a number that does, if I have a variable that doesn't have a number in front of it. I don't have it. So I don't want to solve for y because there's not a y that's almost by itself. And I don't want to solve for x because this has a 6 in front of it and this has negative 4 in front of it. It's going to be a lot of drama for me. So instead I'm going to choose to eliminate one of the variables. And I can eliminate the x's or the y's. For me, in my mind, it's an easier choice to go with these numbers because they're just a little bit smaller. So I'm thinking to myself, okay, great, they have opposite signs already because one's positive, one's negative. So now I'm thinking, what number does 3 and 2, or 3 and 2 go into. 3 and 2 both go into 6. So I'm going to multiply this by 2 to get this to be 6, and this by 3 to get this to be 6. And here's my result. For this top equation, 2 times 6 is 12x. 2 times 3y is plus 6y equals 2. So if you like to do the arrows, that's cool too. Equals 2 times negative 9, which is negative 18. And then 3 times negative 4x is negative 12x. 3 times negative 2y is negative 6y. Equals 3 times 6. I'm sorry, that was 3 times 2. Bam. 3 times 6 is 18. So what's 12x minus 12x? Nothing. What's 6y minus 6y? Nothing. But we need a placeholder here. So nothing is equivalent to 0. Make sure you put that 0, because some people will still put an x or still put a y because we're used to having that. We don't have it this time. Accept it. And then negative 18 plus 18 is also 0. So based on that first slide that you had on the back side of this piece of paper, would this be no solution, one solution, or many solutions? Well, 0 does equal 0. It's a known fact. And so because the statement is true, I'm going to say that this has many solutions. And I would be right. So these are the special cases, and these are only the special cases. You already know how to do it if there's one solution, because you did that in 7.3, 7.4, 7.2, and 7.1. This is only for when you have a special case, and that's what these were. And in your homework tonight, you will have some special cases, probably most special cases, but you'll also have some where you have one solution. And for those, if you get stuck, go ahead and refer back to your notes for 7.1, 2, 3, or 4. Thank you so much for joining me. If you could please start your homework or begin working on your project now. Thank you.